All right, so for example number 2, what do we have? So this is my advice again, write the part of the integral containing the radical as something squared minus another something squared. That is, let me write this as x squared, that is outside, just leave it x squared. And write this as the quantity whose square is 4. What quantity is that? 2, and minus the quantity whose squared is x squared, that's just x. Alright, so this means, and in this case, well, notice, okay, do we have a sum of squares or do we have a difference of squares in this case? It's a difference of squares, so that means the first term is going to represent the largest value, which is the largest length of the triangle. What side is that? The hypotenuse, all right? The hypotenuse. So let's label, that's the hypotenuse, and that's going to be one of the sides. And well, of course, you have two options for the sides because there's two sides. However, my advice is that you use the side that is opposite to the angle actually. So if this is your reference angle, well, let's label the hypotenuse, which in this case is this 2 right here, and the side, which is x. Well, if you do Pythagorean theorem, if you spend all this whole time doing the Pythagorean theorem, again, you will get to this radical, so just write down the radical. No need to do the Pythagorean theorem. And well, so from here, let's make a substitution for the radical. So number 1, from the right triangle that we have a couple of options to relate a couple of quotients. Number 1, we can write radical over 2 or radical over x. However, one of those two is simpler than the other. Which one is the simplest of them? Radical over 2? Okay, so radical over 2 it is. So that is the square root of 4 minus x squared divided by 2. And well, what trigonometric function is that? Cosine, because isn't that adjacent over hypotenuse? So that's cosine theta, and that means let's solve for the right triangle. I mean for the radical. That's 2 cosine theta. So that's the first the piece of information that we need. Number 1, an expression for the radical. We got that part. Okay, so we need to find a substitution for the dx part. Well, again, keep in mind that dx comes from differentiating x. That means we will have to find a quotient involving x. And there's a couple of options. Number 1, x divided by the radical, which I think it's too complicated, and x over 2, which I think it's easier. So let's go with the x over 2. So, and what trigonometric function is this? Sine theta, and x equals 2 sine theta. Now, this is the second piece of information that we'll label in our setup, and we need to find the x by differentiating the x. The x equals 2 cosine theta d theta, and that's number 3. All right. Well, in the previous example, we didn't use number 2. Notice we didn't use number 2 because we didn't have factors of x. We just had the square root of 1 minus x squared. But this time we are going to use the 3 pieces of information in this example. So let me show you how. So number 1, this is the integral of the quantity. Okay, there's a double dx over here. So it should be only one. It's a little typo here. So just for those of you who have the PDF of the handout printed, just scratch it. Okay, so dx is 2 cosine theta d theta All right, but what about the radical? The radical we mentioned, okay, I'm going to leave a space. We got for the radical the quantity 2 cosine theta. Now, outside of the radical, we have this x quantity squared. But we have something for x, which is the second ingredient in the substitution. That is some quantity squared, which is x, and that's 2 sine theta. All right? So, this will be, at the beginning, most of the times these integrals will have a lot of factors of trigonometric functions. However, in many cases, these reduce right away to give us like pretty straightforward integrals. You'll see, like in this case, cosine, or actually the 2 cosine cancels with the 2 cosine, and that leaves us with the integral of, okay, careful here, we need to square the quantity to sine squared. To sine. We square the 2, which is a 4, we square the sine, that's sine squared, and the theta in the numerator. And well, trust me, this will be a very, very simple integral to compute. Well, number one, let's take that 4 in the denominator outside as a 1/4. And well, we cannot integrate this sine squared while it's in the denominator, so we will have to move it to the numerator using our basic identities. So which identity do you think we should use, or what is this equivalent in the numerator? In other words, what's the reciprocal of sine? Not arcsine, that's the inverse function, which is different. Cosecant, all right, so that means cosecant squared the theta. And well, this is one of the direct formulas. The derivative of, or rather, cosecant squared is the derivative of which function? Isn't it cotangent, but actually negative, right? So that's a negative 1/4 cotangent theta plus c. And so we're done solving the problem in the world of trigonometry. Now we need to go back to the world of x, which is the original world this integral was given. So let's see, cotangent from the triangle that we set. What's SOHCAHTOA for cotangent? Adjacent over opposite, that is the radical over x. All right, so that is negative 1/4 adjacent, which is the root 4 minus x squared over x plus c. And well, let's just clean this up. So that's negative root of 4 minus x squared over 4x plus c. Let's do one more example in which the setup will change just very slightly. You'll see. Mm-hmm.
The C.
Uh-huh.
You need to put a line through it. It sounds like 4.
This line?
The one right above it. The C.
Oh, yeah, this is supposed to be plus c, right? Not plus 4. Thank you. Mm-hmm. Thank you. All right, so let's see. Let's look at the next example. Okay, so this time we have the integral of the square root of 9x squared plus 4. All right, number one. The number one thing we need to have a look at is whether inside of the radical we have a difference of squares or a sum of squares. Which one is it this time? It's a sum of squares. So that means, well, when we rewrite the integral, that's okay. Quantity squared plus quantity squared. Well, first of all, what quantity squared is going to give us 9x squared? 3x. And what quantity squared equals 4? Okay, now coming back to what the Pythagorean represents, the way we analyzed last time, what do these two terms represent? Is one of those terms representing the hypotenuse of the triangle this time? What are they representing this time? of them are the sides, right? So does it matter? Well, it doesn't matter which side. Again, I would recommend, or my advice is to have the term that contains the variable to be the opposite to the angle. I mean, you can do it the other way around. You may get integrals using different trigonometric identities, but in the end, you should get the same answer. All right, so let's set up the triangle first. Theta, and well, in this case, the opposite side, so that's a side, and that's also a side, so that's going to be 3x over 2. Yes?
How do you determine those are both side lengths?
Yes, okay, let me go back to what we discussed last time. So this is how the Pythagorean theorem looks like, right? That's hypotenuse squared equals side squared plus side squared, all right? So when you're given the two sides of the right triangle, they're asking you to find the hypotenuse, and when we solve for that equation, it's going to look like a sum of squares inside of the radical. However, there are situations in which you're given the length of the hypotenuse and the length of one of the sides, and the unknown over here would be one of the sides. So you would have to solve for either A or B. All right, it doesn't matter which one you solve for, but the thing here is that you will have the c squared minus a squared, which is hypotenuse minus the side. Now, how do we make sense? How do we make number sense about it? Because, well, the hypotenuse is always the longest of the sides on the right triangle, and not the sides, and we have to get larger value minus smaller value, because if we get it the other way, we would get a negative number inside of the radical, and we will be in trouble there, right? We would get imaginary numbers, complex numbers, right? So 2x and 2, if you do the Pythagorean theorem, that's 3, or rather 9x squared plus 4. And let's do the substitution. Number one, we need an expression for the radical. We have a couple of options. Number one, radical over 2 or radical over 3x. Which one is the simplest of them? Anyone? Which of the two is simplest than one? Radical over 2? Number 2. And what trigonometric function is that? Almost cosine, the other order. So what do we have? We have hypotenuse over adjacent. What's not sine? That's opposite over hypotenuse. Secant. So which is the reciprocal of cosine, right? So secant. And well, let's solve for the radical. 9x squared plus 4 equals to secant. All right. And let's see. The other, okay, we need an expression to obtain the dx, and the dx again comes from differentiating an x. Well, here we no longer have an x by itself. We have a 3x, but it should work anyway. And I'll show you how it works. However, we can relate the 3x over the radical or the 3x over 2. Which of the two is simplest? 3x over 2. Let's go with that. Oh, that, by the way, this is number 1. We got it for the radical. So 3x over 2 equals, in this case, which trigonometric function is that? That's opposite over adjacent. Is that a tangent? Okay, well, from this expression, we're going to solve for x. All we have to do is multiply both sides by 2/3 to get 2/3 tangent theta. And well, let's label this as our number 2. However, we're not going to need it because we don't have factors of x outside of the radical. We still have to write it down because that's what we're going to use to find our dx. Now, what's the derivative? Dx of tangent. Secant squared d theta. That's number 3. And we have everything we need to do the trigonometric substitution. Number 1, that's the integral of dx, which is 2/3 secant squared theta d theta, divided by the whole expression for the radical, which is 2 secant theta, just secant theta, right? Now let's simplify this quantity here. So let's see. Number 1, this. Well, let me write it this way instead, so you can easily see how am I canceling this. So that's 2/3 secant squared theta d theta. Number 1, we can cancel out the 2's right here, and we can also factor 1 power of secant, leaving us with 3 in the denominator, which I'm going to write outside of the integral, and that's a secant theta d theta. Okay. All right, what's the integral of secant? That's one of those formulas that we used in the previous section, a formula that you learned back in Calc 1. Right, one formula that you would be expected to memorize, ln of secant plus tangent plus c. Okay? And well, now that we solved the problem in the world of theta, in the world of trigonometric functions, it's time to go back to the original world of x. So we are going to define the secant expression and the tangent expression based on what we set for our triangle in the original setup. Number 1, secant, which is hypotenuse over adjacent, that is the radical over 2. And tangent, which is opposite over adjacent, plus c. Alright? Okay. So that's final answer for this example. And let's do, I think there's one more, alright? 1 or 2 more, let's see. Okay, the next one, it's a definite integral, and actually it doesn't really look like a radical. So our job, number 1, is to make this look like a radical. So let's see, what do we have? So this time we have the integral of x squared plus 1 to the 3/2. Well, recall that when we have rational exponent, the denominator of the rational exponent indicates the index of the radical. That means in this case we can rewrite this integral from 0 to 1 of the square root of x squared plus 1 and that quantity cubed dx. And now we just turn this into a radical, and well, let's see what do we have for the triangle. So number 1, let's write this as integral from 0 to 1 over square root of quantity squared plus quantity squared. And in this case, well, first we need to write what quantity squared would give us the x squared, which in this case is x, and what quantity squared would give us 1. That's also 1. Well, that was simple. There's really no weird coefficients. So in this case, what do we have? Do we have a difference of squares, or do we have a sum of squares? It's a sum of squares. So that means these two terms will represent what? Hypotenuse by any chance, one of them? Both represent the sides this time, right? So let's see. Oh, that's not an equal yet. Let's triangle theta. Well, again, side, side. Okay, so we can always use the opposite to be the variable, the term that contains the x, and the adjacent, in this case, the constant term. That means the radical term will be the hypotenuse. So from here we're going to do the same again. So we need an expression to replace that ugly looking radical. Well, so we have a couple of options. Divide the radical over x or the radical over 1. Which of the two is the simplest of them? The radical over 1, right? X squared plus 1 over 1 equals to, and that's secant. And well, let me clean this up. X squared plus 1 equals to secant. So that's our number 1 ingredient in the substitution. Now we need something to substitute or to replace the dx and send that dx into its corresponding entity in the world of theta, in the world of trigonometric functions. Well, recall that this dx really comes from differentiating dx. And well, that means we're going to use another ratio, but this time not involving the radical, it's actually involving the x. And well, we have a couple of options again. X divided by the radical, which is ugly looking, or x divided by 1. So how about x divided by 1? And isn't that a tangent? And x equals tangent. That means ingredient number 2 in the substitution. We're not going to need it again because we don't have any factors of x outside. So this is good to find the dx, which is secant squared. And what are we going to have here? Now we're ready to go. We're good to go. So I'm going to skip the limits of integration for now. So what are we going to have? Integral of this radical, which becomes secant, but that quantity is raised to the 3rd power. Forgot to label this as our 3. That times 1 times the dx. So the dx in this case is secant squared. Okay. And well, what are we going to have here? Number 1. Okay, thank you. Secant cubed, secant squared. And see how this reduces really nicely. Cancel the 2 factors of secant in the numerator with 2 out of these 3. So we will remain with 1 factor of secant in the denominator. That means we're going to obtain the integral of secant in the denominator. Well, we don't have an integral for secant in the denominator, but we can use trigonometric identities. What is this equivalent to? And we know the integral of cosine, don't we? That's a really straightforward one. So that's sine plus c. Okay, so we're done with the problem in the world of theta. Now we need to go back to the original world. That's the world of x. And in this case, we only have to evaluate one single trigonometric function. And that's going to be, well, sine, which is opposite over hypotenuse. That is x over radical. So x over the radical. And well, actually not plus c, because this is a definite integral. In other words, this is going to go from 0 to 1. And well, the rest of the problem, it's upper limit minus lower limit. That is 1 over the square root of 1 squared plus 1 minus, well, do we agree that if we plug in the lower limit, this is going to be 0 in the numerator, divided by 0 squared, which is 0 plus 1. Well, whatever that is, it's going to be just a big 0. That's fine. And well, that's 1 over the square root of 1 plus 1, which is 1 over the square root of 2. And you might want to rationalize these values. That's root of 2 over 2. Okay? All right. Okay, guys, so that's essentially what we have for trigonometric substitution. We have plenty of time. I'm going to show you one example on what the book does it, then you will find out whether you will like their method or that method I described here. So I'm going to do the second integral all over again. The book method. Pretty much every single calculus book, actually, that's their approach. Okay, so essentially they just want you to memorize a whole box of information and substitutions, you know. And again, like I mentioned, that's kind of I disagree with that. And actually, the 2 previous semesters I taught this class, I used their approach, but then I found out that this different method, and I like this method better because it saves a lot of time, you know. So what are we going to have? The 3 different cases: u squared minus a squared, u squared plus a squared, u squared. Wait a minute, no, that's the reverse. A squared minus u squared. And so if you have this form, they just tell you use u equals a sine, which means du equals du equals a cosine d theta. If you have this form, essentially they tell you u equals to a tangent theta, which means du equals a secant squared theta d theta. If you have this form, essentially they want you to memorize this a secant theta and du equals a secant tangent. So when looking at this table, I already got annoyed of all this information that I would have to memorize. If I mess up a sign, memorizing all this information, there's a lot of room for making silly mistakes. Well, I'm going to leave this here so we can observe the integral. Well, so what do we have? Oh, in this case, both positives. So that means, oh, this will be the u tangent theta. Okay, so that means that u, well, integral dx over the square root of 3x quantity squared plus 2 squared. This means u equals to 3x and a equals to 2. Going with the substitution, I'm going to write u, which is the corresponding substitution, which is the second one. That's u equals a tangent theta. That is 3x equals 2 tangent theta. From here, we're going to do the dx again in a very similar way. So x equals to 2/3 tangent theta, and you might remember this from the method. So some of the portions of the substitution will be the same the way we did it before. Then we do the dx, which is 2/3 tangent secant squared theta d theta. All right, so we have everything that we need. So in this case, we will replace, check this out, The way the book wants you to do is to replace the 3x with 2 tangent theta, which is going to be here, and that's equal to the integral of dx, which is 2/3 secant squared theta d theta, divided by the square root of 2 tangent squared, just 2 tangent rather, squared plus 4. Okay? I will erase all this. We're not going to need it anymore. And here is the annoying part. Number 1, you would have to simplify this radical. So let me take this 2/3 out of the integral, secant squared theta in the numerator, and 2 squared, that's 4, tangent squared plus 4. Okay, let me continue simplifying this radical to notice the common factor of 4. And that's the square root of 4 times tangent squared plus 1. And the square root of 4, that's equal to 2. Or let me do it here. So that's a 2 radical tangent squared plus 1 and secant squared theta d theta. Alright, well, we can cancel these 2's right here, and well, we need to use trigonometric identities here to simplify the radical. Well, tangent squared plus 1 is secant squared. And then from here, that's 1/3 integral of secant squared theta d theta over the square root of secant squared. That equals to 1/3 integral of secant squared theta d theta over secant. Okay. That triangle we did before to relate, what was that? 3x and 2 and radical 9x squared plus 4. Okay, so this is what we did here. Let me change the color here. So by writing this radical over 2 to obtain the 2 secant theta, I'm saving you 1, 2, 3, 4, 5 annoying steps. Do you feel like doing this all the time? I mean, it's you know the identities. You should be able to know the identities. It's fine, but this quotient, this radical. Oops. Let me use a different color. This radical 9x squared plus 4 over 2, which is secant. It's actually really this term right here. So we're going to go from here straight to here to just simplify all these trigonometric functions before integrating, instead of going through the painful process. I mean, it's not that hard. It's just too time consuming. But again, if you feel comfortable doing this, and when you go back home and read the textbook, you will find out that this is the way they do. Of course, the textbook is going to skip a few steps. I'm writing all the steps for you just to show you what the book does in the background. And ultimately, having radical over number takes you from here to there, and then just integrate. So of course, I mean, I wanted to show you the way I usually prefer doing trigonometric substitutions versus trying to memorize 3 cases you mess up a sign, you mess up the whole problem, you know. And in this case, the way I do it is, the only thing that you need is to understand how the Pythagorean theorem works. Do we have a sum of squares? Well, those are the two sides of the triangle. Do we have a difference of squares? Well, the first term represents the hypotenuse, the second term represents the length of one of the sides. All right?